simulation. Put a resistor there. Control R. This is like the worst UI ever created. And a capacitor. And I'm going to put a voltage source, which is going to be, by the way, the function generator. So I'm going to set the function generator to generate a square wave, so that we can measure the step response of this system. And if this was a mechanical system, then the way you would measure step response is, for example, by applying torque to wheels of a machine, and then measuring how the machine behaves when you apply a step response, like a square wave of the torque. So what is likely to happen is that if you apply a square wave of the torque, the machine would accelerate to a certain acceleration, and when you remove the torque, the machine would decelerate. But for you could just record this first slope of this acceleration, and that would describe the first order dynamics of that mechanical system. But for the sake of this video, it's easier to just create a small RC circuit and do the same. So I'm going to put a voltage source. Let's put a voltage source. And all of this, by the way, is free software. You can just download LTSpice, do your own simulations. Very nice. Apart from the UI that absolutely sucks. So I'm going to connect this. Put two ground connections there. Ground the circuit. And I'm also going to put a little wire here. And then I'm going to set this resistor. I like to use 10K resistors because 10K value is like when you would then measure the capacitance here, then you basically would get the capacitance when you divide by 10,000. So it's very practical to use 10K and not like 2.2K or anything else. And the capacitor I'm going to be using is going to be 2 nanofarads. We can set the function generator to let's see, to a pulse. Initial value is 0 volt. V on, let's say, 4 volts, just because that's what I'm going to be using here in the physical circuit. So like the physical circuit is going to be just a piece of evaluation board, like just a small piece of PCB, and then just capacitor and resistor solder on it. Delay is 0 because that's delay from the start is 0. Rise time could set it to 1 e minus 9. 1 e minus 9. On time could be set for this capacitor to, let's see, maybe 100 microseconds. So that would be 000, 01, and this would be set to 0.0001, maybe 0. Yeah, let's see how this works. So we got that, and then we're gonna run the simulation and see what we get here. We're gonna do transient 0.0, so 1 millisecond simulation. Usually I click this box because it fixes some issues that sometimes arise with capacitors. And then we can just measure this output. We get a output like this. So we need to increase the pulse width here to, let's see, T on can be 0.1, and could run the simulation. That's better. So what we have here is a first order system, a low pass filter, and it has the slope that looks like this. And from this slope, it's even possible to tell the transfer function of the system. A transfer function is a function in frequency domain that describes the dynamics of the system. if we have the transfer function of the system, we can simulate the system, and we can implement different types of filters that depend on knowing the model of the plant. Let's see. It looks like the video is lagging. I'm gonna remove the YouTube window and just do the streaming. So from this picture, I can already tell what the time constant of the system is, and that would be the time it takes for the output of the system to reach 63% of the maximum input, of the maximum output. So 63% of 4 volts would be around 2.52 there. So the time constant is somewhere in the range of, let's see, can we see what that is, of 8 milliseconds. Oh, there we go. So 3, that's precise. So 323, and that would be 0.3 milliseconds. So 0.023 milliseconds. And because we're using such a round value for the resistor, that is actually our capacitance here. So the time constant is determined by the capacitor here, which is 2.2 nanofarads. If we want to identify this system, because obviously it can be more complex than this, we could do it like this. So I have my scope there, and I can turn on the output of the, let's see, of this function generator, and I can also just do this. So it's like, it's a really ugly circuit here. It's just a capacitor and the resistor. But I can measure the signal itself. Let's see. So I'm gonna turn on the output, and and then I'm gonna just configure the function generator to be generating pulses that are the same as in the simulation. Like this, and let's set this to channel 1. And let's see, so like that. And this is the signal generated by the function generator, which is the input, and this would be the, let's see, this would be the output signal. So let's just go back here and just increase this. So looks pretty similar to what we have in the simulation, except that we have a larger period in the simulation. You can do it like this. So we have the input and the output to this network of resistor and capacitor. And if we record both the input and the output, let's see. So I'm gonna just try to sort of have both of them on the screen. So if we record both the input and the output, we can identify the system, and we can identify the capacitance of the capacitor, and we can also simulate this system digitally in C code or in MATLAB or in any other programming language that we want. But before we can do that, we need to identify the system. And for that, I'm going to transfer this waveform onto my computer using an application that talks to the scope. Let's see if I can focus this better. Can I focus this better? So let's turn off autofocus. That's better. A little better. Yeah. Cool. So, and I'm going to bring up a program that can grab the frame from the screen of the scope. And there's a really simple utility called QWriggle that connects over USB to the scope, and we can save the waveform as a CSV file, which makes it easy to work with. So I'm going to export the waveform into let's see, into TLP. Let's create a folder there. And then data CSV, exported number of records. Wait. Let's see. Obviously, I have to freeze the scope. Let's see. Let's do it again. So, waveform, export. So, TMP, data CSV. And now we can load this data into Octave. I'm going to fire up a new terminal. Bigger. So the data looks like this. The beginning of this file for some reason contains like a jump or like an impulse, so I usually just remove it. It's probably due to, I don't know what the effect of that is. It's just that it's always like that. It's always the beginning of the file just contains garbage. And I don't just mean this these two lines. It's the beginning of the data that contains garbage as well. So I remove all of it, and then we can save this file, and we can create view.m, and I use control package and let's see, and the system package, I think it's called signal package. Load package, load control and signal. And these two packages contain all the functions necessary to do system identification and to identify transfer functions. First, I'm going to load the data. So data is CSV read, data CSV. I think that should be enough. Data 0 is going to be, we can just print data, and then we can, let's just do like this. Let's make time is data 0 or data 1. All the indexes start at 1 in Octave, and channel 1 would be data 2, and channel 2 would be data 3, and then we can plot this. Let's see, T channel 1 would be red, and T channel 2 would be black. And just pause the Octave. So, no data. What did I do wrong? I did something wrong here. Let's try this. Okay. Oh. Let's see. Actually, it should be like this. So it's all of the rows in the first, second, and third column, of course. Gotta get the indexing right. So this should work better. So this is the signal that is captured from the scope, which you can see on the picture as well. It actually captures a much longer span of the signal, probably due to how the memory in the scope is set up. So when I do the transfer of the waveform, I get a much longer waveform. But this is workable. So we have stimulated the system with this square wave, and we got as a response, as the system response, we got this filtered wave, and the equation of the system is the transfer function from this input to this output. So if we know the transfer function, we should be able to simulate the system and get a very similar response as the actual measured response here. And this is discrete measurements. So you can see there is some noise there, and there is a certain dt value between the measurements. And also they are not aligned. So before we can do system modification, we need to align these waveforms so that they align more perfectly. So if they're not aligned, then the result will be slightly off. I would ideally need to actually increase the width of this pulse so that I can see where it converges to the actual measurement. Let's see if I can capture a better waveform. So now I can go back here, and I can just remove this header here so I can load the file into Octave. Let's see what we get here. This looks a little better. So here it becomes easier to align the waveforms. So I can see basically that the measurement is slightly lower on the scale here than the input waveform. So I'm going to align them first, and I can actually see from here exactly how much I need to align, 0.05. So let's just do like this, and take the channel 2 would be minus or plus 0.05. Let's see how this works. Are they more aligned? Yes, they're definitely more aligned now. Maybe a little bit more would be nice. 3.07. So let's use this. This is better. So now they're pretty much perfectly aligned. So now we can do system modification. And for that, I'm gonna feed this data into a system identification algorithm, and I'm going to use MOEN2. There are several system identification algorithms that are available in Octave. I'm going to bring this up, MOEN4, I mean, and you can go here, and here's a description of this algorithm. There's also in the package, in the control package, there is a whole set of different algorithms that are available for model identification, and they produce the same models, but sometimes it can be more useful to use a different algorithm. So far, MOEN4 has pretty much always worked for anything that I've done. It's very robust, very nice algorithm. Let's see, 4. So there's AirX, very well known, and then there's MOEN4, MOESP, and 4SID. So basically, MOEN4 is a combination of these two algorithms. So it's kind of the most robust algorithm in this package, I would say. So I'm going to use this algorithm to identify the dynamic model of the capacitor system from the system response. So model would be equal to MOEN4, and MOEN4 takes ID data as the first argument. Let's see. Yeah, ID data set containing the measurements, time domain signals. So you measure the time domain signals of the stimulation and the response, and then you feed them here as ID data. ID data, and the first one is the output. So the output is on channel 2, and we have to transpose this because it expects a vector. And then the input is channel 1, also transposed. I don't think we need this actually. Let's see. And then, because if I put it like this, I can actually have several signals. I don't think actually it will work if I don't do this. Let's see if it works. But the idea is that you can measure several output signals, and you can measure several input signals, and then you can identify the model that describes the relationship between all of those signals from the input to the output. So it's not just limited to a single input, single output models. It can identify any model. And the sample time would be, let's make that dt, and we need the first order model, and we're going to calculate dt like this. It'll be the mean of gradient of t, like this. So the gradient of t is basically the smoothed out derivative of t, and it's pretty much going to be constant because the time step is rather constant. It can vary very little. There's a small variation, but it's like 0.01. So let's see. Let's see if this works. So we get ID data, more inputs than samples. So yeah, we have to supply a list of variables. So a list of transposed inputs and a list of transposed outputs. Let's see. Why is this complaining? Did I do something wrong here? Maybe I was wrong about the transposition. Maybe it's better like this. Yes, apparently it's better like that. Let's see, I'm going to remove the semicolon on the end of the line so that we can see the model. So here's the identified model. And this is, it's very important to see that this is a discrete time system, because if you try to then call, because this is a state space model, if you then try to call state space to a transfer function on this model, on the discrete time model, you're going to get values that are for the discrete model. So that you cannot use those values in a continuous transfer function, the coefficients in a continuous transfer function, because it's going to be completely messed up. So if we want to get the continuous time transfer function, which we want in this case because it's easy from this continuous time transfer function. It's easy to read out the time constant of the system. Then we have to convert this first from the discrete model into continuous model, and then we get the transfer function. But let's validate this model first. So we can simulate this model. We can do like this. We can take output yt equals lsim, and we can simulate this model with the input data from channel 1. And then I guess, I don't think we need dt there though. Let's see. Can we do this? So we can then render t, y, and color would be like green. See if this works. So our simulated model looks very close to the actual measurement data. So this tells us that the identified model is very precise. It's very plausible. It pretty much follows the discrete measurements. And you can see that if we use this model in a Kalman filter, for example, then we are going to get very smooth measurements. We have the potential to get measurements that looks like this instead of the noisy discrete measurements. So models are very useful. So this is the model of this system, and if we want to know the transfer function of this model, we can convert it into a transfer function. Maybe I should explain first what this means here. So this is a discrete model that has a time step of 4 times 10 to the power of minus 7 seconds. And at each time step, basically what this means is that you have the matrix A, so 0.98 times the current state of the system, plus, so it's AX plus BU. U in this case is the input signal, and that is the next state of the system is equals AX plus BU, and the next Y, which is the measurement, is CX plus DU. So the Y is the signal that we plotted in the green line there, right? So this model describes the full dynamics of the system given the input signal, which is U, U1 here. So if we drive this dynamic model with the signal U, we are going to get the response that looks like this, which follows very closely to the measured model. So in Octave, we can then convert this model into a transfer function. But first, as I said, it's very important to convert this to a continuous model. So I do D2C. The function is called D2C, and it takes a discrete model as argument, and it outputs a continuous model. So now we can actually simulate this as well. It's going to be the same result. It's just going to be let's see. Time vector must not be empty. Yeah. So if we simulate a continuous model, we also have to supply the time vector. So yeah, it looks pretty much the same. There is no difference, except now we have a continuous model. And from this model, we can derive the transfer function using the state space to TF, and then we supply the model as the argument to assess the TF, and I think it outputs the coefficients BA, so it's going to look like this. Let's see if this works. Yeah, so we get the coefficients for the transfer function, and to make this more pretty, we can do, so let's see, let's make the function G, TFBA. So this basically converts the coefficients into a transfer function, right? And this transfer function here is very similar to the textbook transfer function of an RC filter. Let's look it up. RC filter transfer function. RC filter transfer function looks like this. So it's V out over V in, which is the relationship of the output to the input, which is what the transfer function describes. It describes how the input controls the output. And the function itself in frequency domain is the V out over V in. And the voltage over the output is basically the model of the capacitor, and the voltage on the input is across the resistor plus the capacitor. And this is what we see here. So what does this actually mean? How can we sort of, let's see. So here's also the simplified model. So the simplified model is 1 over S. So JW is the operator S. So 1 over S times R times C plus 1. And in our identified model, it's a little bit more complex, but it's very similar in the sense that if we just ignore this term, then this term and this term are kind of, they follow the same structure as this equation here. We just need to divide this numerator and denominator by the value of this variable here. So the second coefficient. And we should get very similar, we should get a model that's very similar to the textbook description of the RC circuit model. So let's do like this. Let's take A equals A divided by B2, and B equals B divided by B2. So what do we get now? So we have basically this very, very small value times S here, and that's just the dynamics of the system that we don't really care about. So since it's such a small value, this basically is kind of zero. It doesn't really affect the equations too much. So we can say that the transfer function is 1 over 2.42 to the power of times 10 to the power of minus 5 plus 1. Well, it's like 1.001, but it's kind of 1. Okay. And this constant here, this is our time constant of the system. This is how much time it takes to reach to reach 63% of the output. So we can read it out from the diagram. Let's see. Can I get the diagram here? Let's see. Like this. You can read it out from this diagram here. The time constant of the system. So the time from this point, so let's see, where is that? That's like 0.0015 or 154, and then to the point where the voltage is 2.52, which is 63% of 4. Let's see, 2.41. It's a little bit difficult to just position the cursor there. So let's see, 0.0157. So 0.0157 minus 0.0045. It's going to be pretty close to the result that we got in the transfer function. 0.00157 minus 1.5. It's 2.4 times 10 to the power of minus 5. So it's pretty much this number here. So this is the time constant of this transfer function, or of the system, and based on our known model. So this is the known model of the RC circuit. We can say that R times C equals this number. So this number is basically our 10K resistor times our capacitance value. And so we can basically just say that, let's see, if we divide this by 10,000, we get pretty much like then 2.42 nanofarads. That would be our capacitor value. If we know the resistor, but we don't know the capacitor, from this value we basically can tell our measured capacitance of this capacitor. And we can do this with just about any system. As long as we can excite the system with some test signal, and as long as we can measure the output of the system, using Octave, it's very easy to identify the model of the system. And now, what if we wanted to simulate this model that we just identified? So obviously we can use LSIM, but LSIM is an Octave function. It's not really like we can't really just easily use LSIM in C code, for example. So what if we wanted to simulate this model in C code? Let's say for unit testing, for example. If we have a machine and we need to do some unit testing, we need to know the model of the machine, but we don't really care about the exact dynamics, or like we don't really care about knowing what the model means, but we just need the model. We just need to be able to supply an input and get an output that is reasonably representative of how the real machine would behave. So what do? Well, we can first identify the model here in Octave, and then we can transfer this into C code. So let's do that. And to do that, we need to first, so we need to decide, like the easiest way to do it is to decide first, like what is the time step that you're going to run the model at. And typically like 1 millisecond is very common. You could run your loop at 1 millisecond. And then you can just use discrete model with 1 millisecond time step. Let's see. I wonder if Octave can just resample the model into a specific time step. Can I do that? Otherwise, I'll have to resample the data and just do identification at a given time step. Let's see. Let's actually resample this data. Let's use a fixed DT so that we don't need to do this ugly approximation. We just set DT to 0.0. Let's say in this case it will probably be reasonable to use 1 microsecond because it's a rather fast response model. So 1 e minus 6. And then I'm just going to resample this data to a constant sample rate, which is actually what I should have done when I've been writing the script, because it's very important to have the data in constant sample rate when doing the model identification. It works much better that way. So interp 1, and then we have the t. Let's see, do we need to? Oh, we don't need to do that. Let's see. actually, yeah. Let's just do this linspace. Linspace from 0 to, what would that be? Let's try this. So if I normalize the time to start at 0, so it'll be data 1, 1, this. So now the time starts at 0. And so I can take this linspace from 0 to, I wonder if this would be right. So this would be then t end. Could that be right? Maybe that is right. How many time steps then? So t end divided by t, I guess. That could work. I'll see if that works. And then chan1 is resampled using interp and using I'll make this time. So that would be interp. Let's see what this. How does interp work? So xv and then xq. That would be the, let's see. So this would be time, is the sample times, and then that would be with the channel 1. And I suppose this would be the new sample time. Yeah. So that would be the new sample time. And then channel 2 is interp 1. Time, original sample times for channel 2, and then the new sample times. So this should produce pretty similar results. Let's see, more outputs and samples. Yeah, this was a little wrong. So that's 8,000 rows in one column. Yeah, okay. So we get a transposed vector out of interp 1, so we need to do the transposition here. Yeah, right. So now we're working with fixed time step. We get very similar results. 2.42, low capacitance. Yeah, cool. So now I can transform this model into C code, so I can simulate it in C. And what is this going to look like? Let's see. So first I need to transform the transfer function into a discrete transfer function. So that would be C2D, G, and the sample time would be dt. And so the coefficients of this discrete transfer function are basically coefficients of a difference equation which describes the system. And the difference equation is just an equation that describes how do you combine previous inputs and previous outputs in order to produce next output. And it's an easy way to think about simulating a system in a programming language, where you just sort of run it in time steps, and at each step you kind of take a number of previous values multiplied by coefficients, and then produce the next measurement value based on the previous inputs and previous outputs. Gonna see. And also because the values that are printed, like pre-printed in the by Octave, they're not real. They're kind of rounded, so it's better to also take the B and A and extract them using TF data from B and let's see, from Z, like this, so that we get the more precise values of the coefficients. So this would be the coefficients of the previous, let's see, this would be the x. So this would be the measurements, the previous results of the difference equation, and this would be, let's see, this would be the previous outputs of the difference equation. So the difference, so this would be like previous inputs and previous outputs, and what we want is the output yn, which would be this value. Actually, I'm gonna look this up so that it's explained. Let's see, discrete transfer function to difference equation. Yeah, if you're interested, you can look this up by yourself. But I'm just gonna convert this these values. Just take these values and put them into C code. Let's see if this works. X term should be using non-terminal. How do you copy paste an X term?